Welcome to Dreaming Through Knowledge. Tonight, we travel far beyond the edges of our atmosphere, out into the silent depths of space. There, in the cold darkness between the stars, new suns are waiting to be born. Here, we create calm journeys through science, history, and wonder, stories designed to help you fall asleep a little wiser than when you woke. If you enjoy learning in this quiet way, consider subscribing to the channel. Multiple times a week, we release new long-form explorations, from the depths of the ocean to the edge of the universe. Leave a comment below and tell us what you'd like to explore next. Your ideas shape these journeys. Every suggestion becomes another path through knowledge, waiting to be dreamed. Let's start. When we look at the night sky, the stars appear timeless, fixed points of light that seem eternal. But like everything in the universe, they have beginnings and endings. Each one has a story, a birth, a life, and eventually, a quiet or explosive death. To understand how stars are born, we must begin with their raw material, the vast clouds of gas and dust scattered between the stars, known as nebulae. To the human eye, they appear as faint smudges or glowing curtains of color, but in truth, they are immense, some stretching across hundreds of light years. These clouds are mostly hydrogen, the simplest and most abundant element in the cosmos. Mixed within it is helium, a trace of heavier elements, and countless particles of dust, tiny fragments of carbon, silicon, and ice. This interstellar dust drifts quietly through the galaxy, invisible yet essential, for within it lies the seed of every future star and planet. In the beginning, the gas and dust are diffuse, spread so thinly that a cubic meter may contain only a few atoms. Yet gravity is patient. Over millions of years, its gentle pull begins to gather matter together. Small regions within the cloud start to clump, drawing in more mass as they grow denser. Where the density increases, gravity strengthens, and the collapse accelerates. This self-reinforcing process is known as gravitational contraction. It is the quiet heartbeat of creation, the invisible rhythm that builds suns. Astronomers call these regions molecular clouds because within them, hydrogen atoms pair up to form molecules. These molecules can cool the cloud efficiently, allowing collapse to continue without overheating too soon. In that delicate balance between gravity and temperature, stars begin to take shape. The first stage of birth is subtle. Within the larger nebula, small knots of matter, called protostellar cores, form under their own weight. Each core spins slowly as it collapses, conserving angular momentum. Around it, a flat disk of dust and gas begins to form. At the center, pressure rises. As atoms are squeezed together, their motion creates heat. The temperature climbs from near absolute zero to thousands of degrees. Eventually, the growing sphere begins to glow faintly in infrared light, invisible to our eyes, but detectable by telescopes. It is not yet a star, but its first light has begun. These young objects are called protostars. They are cocooned within thick blankets of gas and dust, hidden from optical view. For millions of years, they continue to contract and heat, fed by streams of material from the surrounding disk. During this time, powerful jets of gas shoot from their poles, carving tunnels through the nebula. These jets, observed in glowing patterns called Herbig-Haro objects, mark the violent early breaths of a newborn star. As more mass falls inward, the pressure at the core climbs until the temperature reaches around 10 million degrees Celsius. At that threshold, something extraordinary happens. Nuclear fusion begins. In fusion, hydrogen nuclei combine to form helium, releasing vast amounts of energy in the process. That energy pushes outward, counteracting the pull of gravity. For the first time, the collapsing cloud finds balance, inward pressure matched by the outward force of light. A star has been born. From this point on, the newborn star shines steadily, no longer a secret within dust, but a beacon of visible light. The surrounding material, warmed by radiation, begins to disperse, revealing the young sun to the galaxy. If we could drift among these regions, we would find beauty on scales beyond comprehension. Some nebulae glow red with hydrogen emission. Others shine blue, where starlight scatters off fine dust. Still others appear dark, silhouetted against the luminous background, cradles of stars yet unborn. One of the most famous is the Orion Nebula, visible to the naked eye as a fuzzy patch in the sword of Orion. It lies about 1,300 light-years from Earth and contains thousands of young stars forming within a vast cloud of gas and dust. Astronomers have studied it for centuries, yet it continues to reveal new secrets about the birth of suns. Another is the Eagle Nebula, home to the towering pillars of creation, captured in breathtaking detail by the Hubble and James Webb Space Telescopes. These columns of dust stretch for light years, sculpted by radiation and wind from nearby massive stars. Within their shadowed interiors, smaller stars are forming, protected from the harsh light around them. The process that gives rise to stars is both violent and gentle. Gravity pulls inward relentlessly, while radiation pushes outward, carving structures of intricate beauty. The result is a dynamic balance, a dance between collapse and creation. Even within a single nebula, not all stars form the same way. Some become small, cool red dwarfs, steady, long-lived and faint. Others grow massive, burning bright and fast before exploding as supernovae. The mass of the collapsing core determines the destiny of each star. In smaller cores, fusion begins quietly, and the star may live for trillions of years. In larger ones, fusion races ahead, consuming fuel rapidly and creating heavy elements that will later enrich future generations of stars and planets. Star formation is not a single event, but a continuum. At any moment across the galaxy, countless stars are in every stage of birth, some mere whispers of gas, others already shining. Our Milky Way produces several new stars each year, each one a spark in the long story of cosmic renewal. From a scientific perspective, the forces at work are described by simple equations: the law of gravity, the conservation of angular momentum, the thermodynamics of fusion. But behind the mathematics lies a deeper harmony. The same principles that shape galaxies also shape the atoms in our bodies. The hydrogen fusing in distant stars is the same hydrogen that fills our oceans and our blood. We are made of the universe's first element rearranged by time. In this way, star birth is not only an astronomical process but a personal one. Every atom heavier than hydrogen, the carbon in our cells, the calcium in our bones, the iron in our blood, was forged inside an earlier generation of stars. Those stars lived, burned, and died, scattering their enriched matter into space. From that debris, new clouds formed, new stars ignited, and new worlds coalesced. we are part of that lineage, children of stellar alchemy. The newborn stars we see today are the next link in that unbroken chain. They will one day create new elements, new planets, perhaps even new life. Each star is both a continuation and a beginning, light remembering itself. Through telescopes, astronomers study these nurseries in every wavelength of light. Radio telescopes reveal cold hydrogen clouds. Infrared instruments peer through dust to glimpse hidden protostars. X-ray observatories detect the fierce energy of young suns. Each window shows a different aspect of creation. Yet for all our knowledge, the experience remains awe-inspiring. To imagine a sphere of gas collapsing under its own weight until it ignites is to glimpse the raw power of the cosmos. In the next chapters, we will explore what happens after this moment of ignition, how stars live, evolve, and shape their surroundings, and how the story of their light continues into the atoms of life itself. For now, let us linger in the nebula's quiet glow. Among drifting dust and embryonic suns, time moves slowly, almost imperceptibly. Creation here is not sudden. It is patient, unfolding over millions of years. Somewhere within that vast silence, a new star is forming at this very moment. Its light will not reach us for centuries, yet it already exists, a promise written in gravity and gas. The universe, in its stillness, continues to create. And from that creation, everything we know, every spark, every planet, every breath, is born. In the heart of a young star, a quiet revolution begins. The immense weight of gas and dust has collapsed inward, compressing hydrogen into something new, a furnace of light that will burn for billions of years. At around 10 million degrees Celsius, the pressure becomes so great that the simplest atoms in the universe are forced to join together. Protons fuse to form helium, releasing energy in the form of light and heat. This process, nuclear fusion, is the power source of every star that has ever existed, from the faintest red dwarf to the brightest blue giant. For millions of years, the protostar struggled to balance gravity's pull against its own rising pressure. Gravity tried to crush it into a smaller and smaller sphere, while the heated gas inside pushed outward, fighting collapse. Now, with fusion ignited at the core, a new equilibrium has been reached. The star stabilizes, shining steadily as it enters what astronomers call the main sequence, the long middle chapter of stellar life. In this phase, the outward push of radiation perfectly counters the inward pull of gravity. It is a delicate harmony, sustained for billions of years, as hydrogen slowly transforms into helium deep within the star's core. Our own Sun is one such main sequence star. It has been burning in this steady phase for roughly 4.6 billion years and will continue for at least 5 billion more. During this time, the balance of forces keeps it stable, luminous, and life-giving, a constant presence in the sky of a small, rocky planet. But the story of starlight is not confined to the core. From the fusion zone deep within, energy must journey outward through layers of plasma before escaping into space. This journey is slow, intricate, and astonishing. A single photon created in the sun's center can take tens of thousands or even hundreds of thousands of years to reach the surface. In the core, matter is so dense that light cannot travel in straight lines. Photons bounce randomly from atom to atom, absorbed and re-emitted countless times. They change direction with every interaction, wandering like a lost traveler through a crowd. By the time a single photon finally escapes into open space, its origin is ancient. Outside the core lies the radiative zone, a region where energy is still carried mostly by radiation. Here, photons continue their random walk, diffusing slowly outward. Farther out, in many stars including the Sun, lies the convective zone, where energy moves in a different way. In the convective zone, hot gas rises toward the surface, cools and sinks again, forming vast rolling cells of motion. This process is similar to boiling water in a pot, but on a scale larger than entire planets. These currents carry energy far more efficiently than radiation alone, and they shape the surface of the star. On the visible surface, or photosphere, these convective cells appear as granules, bright patches surrounded by darker edges where cooler gas descends. Each granule on the Sun can be as large as a continent, bubbling and fading in minutes. From this shifting surface, energy finally radiates freely into space, spreading out in all directions as starlight. From the surface, this energy travels at the speed of light. 8 minutes after leaving the Sun, it reaches Earth, warming oceans, feeding plants, and sustaining the fragile balance of life. On more distant worlds, the same radiation might warm icy moons, sculpt atmospheres, or shine on barren rock. Every star in the universe performs a similar transformation. Each turns gravity's inward collapse into outward illumination, order arising from what could have been chaos, structure emerging from simplicity. Stars are not simply glowing balls of gas. They are engines that convert mass into energy, turning potential into presence. Stars are not isolated points. They are architects of galaxies. Their light and gravity sculpt the clouds around them, forming patterns of motion and matter. Young stars heat nearby gas, creating bubbles and filaments that ripple through their birthplaces. These cavities and ripples act as signposts, showing where energy has flowed. As groups of stars ignite within the same nebula, their combined energy shapes their environment even further. Winds from massive stars sweep away gas, triggering the formation of new stars in compressed regions beyond. In this way, one generation gives birth to another, and stellar nurseries become neighborhoods of related suns. This chain reaction of creation and transformation builds the structure of galaxies over time. The Milky Way, for example, is a vast ecosystem of star birth and death, a self-renewing spiral of light stretching about 100,000 light-years across. Within its arms, waves of star formation move like slow tides, igniting regions and leaving behind clusters and remnants. Within this galactic cycle, stars vary enormously in size and brightness. Some are small, cool red dwarfs that burn their fuel slowly and live for trillions of years. Others are blue-white giants, burning with furious intensity, destined to survive only a few million years before they collapse. The size of a star determines almost everything about its life. Mass sets a star's temperature, color, lifespan, and eventual fate. The smallest stars shine faintly, their fusion gentle and efficient, sipping hydrogen slowly. The largest blaze brilliantly, pushing their limits, living short and dramatic lives. In this way, stars are like candles of different thicknesses, each burning according to the amount of wax within. Astronomers classify stars by their spectral type, a sequence described by the letters O, B, A, F, G, K, and M. These letters, though they may seem arbitrary, are arranged from the hottest to the coolest. O-type stars are the hottest and most luminous. M-type stars are the coolest and faintest. Our Sun is a G-type star, moderately warm and yellow in color, occupying a stable middle ground between power and longevity. Massive O-type stars burn at tens of thousands of degrees and shine millions of times brighter than the Sun. Their ultraviolet radiation ionizes nearby gas, causing nebulae to glow in vivid colors. They are rare, but dominate their neighborhoods, shaping everything around them through intense radiation and strong stellar winds. At the other end of the scale, M-type red dwarfs are dim, but numerous. They make up the majority of stars in the Milky Way. Though too cool and faint to see easily with the naked eye, their combined light fills the galaxy with quiet persistence, a background of steady embers beneath the brighter flames. The diversity of stars forms the raw material for cosmic evolution. When a star forms, it begins to enrich the universe by producing new elements through fusion. At first, it creates only helium from hydrogen, but in more massive stars, the process continues, forming carbon, oxygen, and heavier atoms in concentric shells deep within the core. Inside a massive star, these shells resemble the layers of an onion. Hydrogen fuses in the outermost active shell. Helium fuses in a deeper layer, and heavier elements form closer to the center. Each step of fusion releases energy and supports the weight above, holding back gravity's grip a little longer. Each stage of fusion requires higher temperatures and pressures. At the most extreme, massive stars can forge elements all the way up to iron. Beyond iron, fusion no longer releases energy. Instead, it consumes it. At that point, the delicate balance between gravity and pressure begins to fail, setting the stage for a future collapse. But that part of the story, the death of stars, will come later. For now, the young main sequence star shines in peace. Deep in its core, hydrogen fuses steadily into helium. Around it, layers of plasma carry that energy outward. At its surface, photons stream into space, forming the glow we see as starlight. Rate 100%, pitch 1%. This radiation does more than light the darkness. It defines regions around the star where conditions might one day allow life. Astronomers call this region the habitable zone, the distance where a planet could maintain liquid water on its surface, given a suitable atmosphere. The size and position of this zone depend on the star's luminosity and temperature. Around small red dwarfs, the habitable zone lies very close in, where planets may become tidally locked, with one face always turned toward the star. Around bright, hot stars, the habitable zone lies farther away, but these stars often live too briefly to give complex life time to evolve. Moderate stars like the Sun offer a long window, billions of years in which chemistry can explore the possibilities of life. Around many stars, leftover material from their birth forms a disk of dust, rock, and ice. Within this disk, particles collide and stick together, building larger and larger bodies. Over millions of years, this slow accretion sculpts planets, moons, and asteroids, each one a small archive of the star's early environment. The orbits of these worlds remember the spin and tilt of the original cloud. They move in flattened planes, circling their parent star in near ellipses, held by gravity and guided by momentum. In some systems, giant planets migrate inward or outward, reshaping the layout of the entire family. The architecture of a solar system is a fossil of its star's youth. Within the star itself, invisible processes continue. Magnetic fields rise and fall as plasma moves and twists. On the Sun, these fields create sunspots, darker and cooler regions on the surface, as well as flares and coronal mass ejections that release bursts of energy and charged particles into space. These events form what we call space weather. On planets like Earth, they can produce auroras near the poles, shimmering curtains of light created when charged particles interact with the upper atmosphere. At the same time, strong bursts can disturb satellites and electrical systems, subtle reminders that our technology lives beneath the changing moods of a star. Astronomers study the interior of stars like the Sun through a field known as helioseismology. By observing tiny oscillations on the surface, they infer how sound waves move through the interior, revealing density and temperature at different depths. It is similar to how geologists use earthquakes to probe Earth's inner structure. From this, we learn that stars are not static objects, but dynamic, vibrating spheres of plasma. Waves move through them, magnetic fields shift, and energy flows constantly from core to surface. Even in apparent stillness, a star is full of motion. When we observe the night sky, we are seeing stars of every age along the main sequence. Some are just beginning their stable lives, others are nearing the end of their hydrogen supply. Their colors, brightness, and spectral lines reveal where they stand in this long progression. The light of stars carries information about their nature. By splitting starlight into its spectrum, astronomers can determine temperature, composition, and motion. Dark lines within the spectrum reveal which elements are present, such as hydrogen, helium, oxygen, and iron. This technique, known as spectroscopy, allows us to read the chemistry of the universe as though it were written in color. Each star's spectrum is a signature, a record of the processes at work within it. From that signature, we can tell whether a star is young or old, fast spinning or slow, calm or active. We can even detect the presence of planets, revealed by small, regular wobbles in the star's motion or by slight dips in brightness when a planet passes in front. Through this knowledge, humanity has learned that all stars share the same fundamental building blocks. The elements that compose distant suns are the same as those that compose us: hydrogen, helium, carbon, nitrogen, oxygen, and heavier elements appear again and again across the cosmos. The universe, in its vastness, is made of familiar material arranged in extraordinary ways. The radiation from stars also shapes their surroundings in subtle ways. Ultraviolet light ionizes gas, stripping electrons from atoms and creating glowing nebulae. Solar winds carry charged particles far into space, sculpting magnetic fields and influencing the formation and evolution of planetary atmospheres. These winds inflate vast bubbles around stars, known as astrospheres. In some regions, the pressure from stellar winds compresses nearby gas clouds, triggering the next cycle of star formation. Creation breeds creation. Light gives rise to more light. The main sequence phase is therefore not only a period of quiet burning, it is a time when the star actively reshapes its environment and participates in the wider ecosystem of the galaxy. This continuous recycling of matter is one of the universe's most elegant patterns. There is no absolute beginning or final end in the life of matter, only transformation. Hydrogen becomes helium, helium becomes carbon, and in time those atoms become part of new systems, new stars, and new lives. Stars also connect the scales of existence. A single star is both local and cosmic. It warms the space around it while contributing to the structure of an entire galaxy. In their collective light, galaxies glow, islands of brilliance adrift in the dark of space. As we study them, we also learn about ourselves. The same physical laws that govern the heart of a star govern the cells in our bodies. The flow of energy, the balance of forces, the transformation of one form into another. These are universal themes. Energy cannot be created or destroyed. It changes shape, moves, and continues. Astronomers often describe star formation and stellar life as the universe's way of turning darkness into radiance. But perhaps it is more accurate to say that stars reveal what was always possible, the potential for light within matter. They take simple ingredients and arrange them into enduring brilliance. Each time we gaze upward, we see the results of billions of years of these quiet, patient processes. Light that began its journey before human history shines upon us now, unchanged and unhurried. The stars we see are not only distant suns, they are ongoing experiments in balance, continuously holding gravity and radiation in a fragile truce. The stars we see are more than distant points of light. They are messages written in photons, telling us that the universe is alive with transformation. Their glow crosses time and space, carrying the story of its own making. In that story, the main sequence is the longest and calmest chapter, a time of stable radiance before the more dramatic events to come. In the next chapter, we will travel further along the path of stellar life. We will see how the balance begins to change when hydrogen in the core is finally exhausted, how stars swell into giants or rush toward collapse, and how their endings seed the cosmos with the elements of worlds and living beings. For now, let us rest with the image of a young star in its prime. Hydrogen fuses quietly at its center. Light flows outward in endless streams. Planets circle in slow, graceful orbits. And across the gulf of space, that steady glow reaches us, a calm reminder that in the heart of the cosmos, balance is possible. Every star, no matter how large or small, lives according to the same quiet law, the balance between gravity and light. For millions or billions of years, this balance holds steady, a gentle arrangement that keeps each star bright and stable in the darkness. But nothing in the universe remains unchanged forever. Even while a star appears constant, the fire within slowly shifts. Hydrogen, the simplest fuel in the cosmos, is gradually consumed. The core becomes heavier with helium, while the outer layers continue to glow with the energy of fusion. As the chemistry of the interior changes, the star begins a slow transition toward its next chapter. Over vast stretches of time, the balance that defines a star begins to drift. When the hydrogen in the core runs low, fusion slows. Gravity, always patient, begins to press inward again. The star must respond or collapse. To resist this growing pressure, the star adapts in a remarkable way. Fusion moves outward into a shell around the core, while the inner region contracts and heats. This change transforms the structure of the star, and prepares the way for the next stage of its life. The entire internal architecture is rearranged by the simple fact that one element has become another. As the core contracts, the outer layers expand. The star swells to many times its original size. Its surface cools as it grows, and its color shifts from white or yellow toward a softer orange, and eventually a deep red. What was once a stable sun becomes a red giant, a luminous and swollen version of its younger self. Our own sun will follow this path billions of years from now. It will grow large enough to engulf Mercury and Venus. The light that warms Earth will become redder and more diffuse. Eventually, its outer layers will drift away into space, forming a delicate cloud of glowing gas known as a planetary nebula. At the center of that cloud, a small, dense core will remain. That remnant is a white dwarf. It is no larger than Earth, yet contains nearly half the mass of the Sun. It glows faintly from leftover heat, but does not produce new energy. Over billions of years, the white dwarf cools, fading slowly into darkness. In that silence, the matter that once formed a star waits to be recycled into future generations of suns. This is the fate of medium-sized stars like our Sun. It is a quiet ending compared to the more dramatic destiny of stars that begin their lives with far greater mass. These massive stars burn with fierce intensity and age quickly. Their path leads to some of the most powerful events in the universe. In the cores of massive stars, the temperatures and pressures are so extreme that fusion proceeds beyond helium. Hydrogen becomes helium. Helium becomes carbon. Carbon becomes oxygen, then neon, then silicon in successive layers deep within the star. With every transformation, the core contracts and heats until it reaches the final barrier. That barrier is iron. Fusion of iron requires more energy than it releases. When the core fills with iron, fusion stops and gravity wins in an instant. The core collapses so quickly that the outer layers rebound and explode outward in a supernova. It is one of the brightest and most violent events ever seen in the cosmos. A supernova can outshine an entire galaxy for a brief moment. Its shock waves pulse through surrounding space, compressing gas and triggering new rounds of star formation. Its light travels for millions of years across the universe, a final message from a star that has already died. In that explosive chaos, the universe performs its most creative act. The extreme pressure and heat forge the heaviest elements known: gold, silver, platinum, uranium. These rare materials are born in the final breath of a dying star. The blast hurls these elements into space, enriching the surrounding clouds of gas and dust. Over time, those clouds cool, collapse, and form new stars and new planets. Each generation becomes richer in complex material than the one before. This slow enrichment shapes the chemistry of galaxies and eventually allows planets like Earth to exist. From the debris of these explosions come the ingredients for everything solid and living: the iron in blood, the calcium in bones, the gold in rings. All were created inside ancient stars that died long before our world formed. At the center of a supernova, something extraordinary remains. If the collapsing core is between about 1 and 3 times the mass of the Sun, it becomes a neutron star. A neutron star is tiny, yet unbelievably dense. A teaspoon of its material would weigh billions of tons. Its magnetic fields and rotation create beams of radiation that sweep through space like cosmic lighthouses. Astronomers call them pulsars. If the core is even more massive, gravity crushes it further. Nothing can stop the collapse. A black hole is born, an object so compact that not even light can escape its pull. It reveals its presence only through its effect on nearby stars and gas. Invisible yet powerful, a black hole represents gravity at its most extreme. Across the universe, black holes and neutron stars serve as reminders that creation and destruction are inseparable. These objects are not failures of nature. They are the natural consequences of the same laws that form galaxies, worlds, and life. They mark the places where physics reaches its limits and where matter is transformed. Not all stars end in explosions. The smallest and dimmest red dwarfs lead quiet lives. They burn their hydrogen so slowly that none have yet reached their end since the universe began. In time, they will fade into blue dwarfs, and eventually into cold, invisible remnants known as black dwarfs. To study the lives of stars is to study time itself. Each type, from dwarf to giant, marks a different rhythm in the universe. Some lives unfold in quick, dramatic bursts. Others stretch across aeons. Yet all follow paths determined by mass, the single factor that decides temperature, brightness, and fate. Astronomers use a tool known as the Hertzsprung-Russell diagram to chart these lives. It plots stars according to their brightness and temperature. On this map, young stars cluster along the main sequence. Giants and supergiants rise above. White dwarfs fall below. The diagram reveals the order behind the apparent chaos of the night sky. This diagram tells a profound story. Stars, despite their differences, follow universal rules. Their behavior and evolution can be predicted from mass alone. In the language of physics, destiny is written in weight. The study of stellar evolution has also revealed that the universe itself evolves. When the first stars formed billions of years ago, the cosmos contained almost nothing but hydrogen and helium. Each generation of stars added new elements to the interstellar medium. This accumulation of heavy elements made possible everything complex: planets, oceans, life. The night sky is not a collection of frozen lights. It is a living mosaic of ages. Each point of light represents a stage in the cycle of birth, growth, transformation, and renewal. Some stars we see are already gone. Others have yet to fully form. When we look upward, we see not a single moment, but many layered together. Starlight is a form of memory. It records the universe across billions of years. To observe it is to read the autobiography of existence, written one photon at a time. Even as stars evolve, their influence continues. Their winds sculpt gas. Their deaths seed galaxies. Their light shapes the chemistry of worlds. Stars are the universe's gardeners. They tend the raw material of space, cultivating new stars and new planets. Their deaths plant the seeds of the next generation. This cycle of enrichment and renewal gives galaxies their character and complexity. Across vast distances, astronomers observe galaxies in every stage of this process. Young galaxies glow, blue with hot, massive stars. Older galaxies shine red as their giants fade. Color becomes a language of time, a way to see history written in cosmic light. Among all these cycles, our sun shines quietly in the middle of its life. Stable and generous, it provides the light that makes Earth habitable. For billions of years, its energy has shaped the chemistry of our planet and the evolution of life. In every breath and every heartbeat, the energy of the sun flows. We are not separate from stars. We are shaped by their histories. The boundary between cosmic and human is one of scale rather than substance. Everything we are comes from processes written in the hearts of stars. In the next chapter, we will follow the journey of starlight itself. We will see how light travels across space, how it becomes color and warmth, and how it carries with it the information that allows us to understand the universe. For now, imagine the slow pulse of the cosmos, countless stars aging, changing, and passing their essence onward. It is a cycle without hurry, a rhythm that echoes across galaxies. The life of a star is long and complex, yet its story is the same everywhere. Birth in dust, growth in light, transformation in death, and renewal in the next generation. Light begins in silence. It forms in the hidden places of the cosmos, deep within the hearts of stars and in the glowing embers of distant galaxies. Before it emerges into the open universe, it endures a long and crowded journey through matter so dense that its path becomes a maze. What we eventually see as a simple point of brightness in the sky has already lived lifetimes inside a star. Light is the oldest traveler we know. Every photon, no matter how faint, carries the memory of its origin. It drifts across the dark with perfect constancy, revealing the story of the universe to any eye prepared to receive it. To understand this journey, we return first to the core of a star. Here, temperatures rise above 10 million degrees and atoms collide with such force that they merge. Hydrogen becomes helium, and in the process, energy is released. That energy begins as a photon, a small packet of light. This newborn photon cannot move freely at first. Inside a star, matter is packed so tightly that light is absorbed and re-emitted again and again. Its path resembles a random walk, a slow wandering through layers of plasma. The time a photon spends inside a star can be astonishing. It may take thousands or even millions of years to reach the surface. What begins as a moment of creation becomes a long pilgrimage toward freedom. Only once it escapes the star's outer layers can the photon travel unobstructed through space. When the photon finally leaves its star, its journey becomes simple. It moves at the constant speed of light, unaffected by the vacuum around it. There is no friction, no resistance, no slowing with distance. It continues forward until it meets something that can absorb or reflect it. Light travels in straight lines unless it encounters gravity. This surprising truth reveals another layer of cosmic structure. Gravity bends space itself, and light follows that curvature. When light passes near a massive object, its path warps slightly. Astronomers call this gravitational lensing. Through this effect, galaxies behind other galaxies appear stretched or magnified. Light that began its journey billions of years ago can be redirected by the weight of the cosmos. The universe becomes its own lens, shaping the view across unimaginable distances. Beyond stars, light emerges from other sources as well. Nebulae glow when their gas is energized by nearby suns. Supernovae shine with the force of entire galaxies. Even the faint background radiation that fills all of space is a form of ancient light, a relic of the early universe. Each wavelength of light tells a different story. The visible spectrum is only a small fraction of what exists. Infrared reveals heat. Ultraviolet carries higher energy. X-rays and gamma rays show the violent processes near black holes and exploding stars. Radio waves reveal the cold and quiet places where new stars are born. Astronomers use instruments tuned to different kinds of light to explore the universe. A radio telescope sees long waves that travel through dust. An infrared telescope sees through thick clouds where new suns take shape. The most energetic forms of light reveal collisions and extremes that shape galaxies. Each type of light becomes a tool for understanding the cosmos. The spectrum is a language, and astronomers have learned to read it. Dark lines within a spectrum reveal which atoms are present. Bright lines show energy transitions within those atoms. Through this reading of light, we know the chemistry of stars we cannot touch. We can measure their temperature, their age, and their motion. The color of starlight shifts depending on whether a star moves toward us or away. This shift, known as redshift or blue shift, becomes a measure of cosmic expansion. It was through redshift that astronomers discovered one of the most profound truths. Galaxies are drifting apart, and the farther they are, the faster they recede. The universe itself is expanding. Light revealed this hidden motion by stretching as space stretched. Light does not simply show us the universe as it is now. It shows us the universe as it was. Because light takes time to travel, everything we see in the night sky is already in the past. The moon is seen as it was 1 second ago. The sun as it was 8 minutes ago. Distant galaxies as they were millions or billions of years ago. Telescopes are therefore windows into history. Looking far enough into the distance means looking back to the beginning of time itself. The faint glow known as the cosmic microwave background is the oldest light we can detect. It was released when the early universe first became transparent. From this ancient light, scientists learned the age, shape, and evolution of the cosmos. The temperature of the background radiation is nearly uniform, but tiny variations reveal the seeds of galaxies. Light carries this memory with quiet precision. On Earth, we encounter light in more familiar forms. Sunlight warms the planet, drives weather, and fuels life. Plants capture photons from the sun and store their energy through photosynthesis. Animals and humans rely on that stored energy in every breath and heartbeat. Light interacts with Earth's atmosphere in ways that shape color and climate. Shorter wavelengths scatter more easily, filling the daytime sky with blue. At sunset, when sunlight passes through thicker air, the blue is scattered away and reds and oranges remain. Starlight twinkles because of the same scattering. Turbulent layers of the atmosphere bend the light slightly as it reaches our eyes. This flickering effect, though beautiful, reveals the dynamic and ever-changing nature of air above us. Light is also the foundation of vision. When a photon enters the eye, it strikes cells in the retina that convert it into electrical signals. These signals travel to the brain and become sight. In this way, the oldest traveler in the universe becomes awareness. Every act of seeing links us to the cosmos. Light that formed in distant places completes its journey in the human mind. The universe becomes conscious of itself through this encounter. Yet not all light reaches us. Some is absorbed by dust between stars. Some is captured by planets or reflected back into space. Some falls into black holes, never to escape. Even in those losses, light influences the universe. Absorption warms dust and gas, changing their behavior. Reflection paints worlds in color. and the light that spirals into black holes heats matter to such extremes that it becomes visible in X-rays. Black holes, though they trap light within their event horizons, create some of the brightest phenomena in existence. Matter falling toward them forms a disk that becomes unimaginably hot. This disk radiates energy and becomes a beacon that reveals the otherwise invisible presence of the black hole. Light, therefore, helps us detect the darkest objects in the cosmos. The absence of light, paired with the presence of high-energy radiation, becomes a signature of these extreme environments. Light also shapes time. Einstein showed that the speed of light is constant for all observers, which reshapes how time and space behave. No matter how fast something moves, light always travels at the same speed. This constancy weaves an order into the structure of reality. As objects move faster, time slows for them. As they climb out of deep gravitational wells, time accelerates slightly. Light becomes the reference by which all motion is measured. There is a quiet beauty in this. The same light that illuminates night skies also defines how the universe keeps its rhythm. Every second, every moment, is connected to how light moves through space. Some of the most delicate effects of light appear close to home. Rainbows form when sunlight refracts through droplets. Auroras glow when solar particles excite atoms in Earth's atmosphere. Even shadows carry information about the direction and quality of light. Light is woven into the rhythms of Earth. The rise and fall of daylight shapes sleep and wakefulness. Animals migrate by the position of the sun and stars. Plants open and close their leaves according to the changing glow. The biosphere is driven by the constant arrival of photons. Without this steady influx of energy, Earth would be cold and lifeless. Every movement of wind and wave owes something to the sun. When we look at starlight, we participate in a relationship that spans eons. Those photons may have begun their journey before humanity existed. They traveled across empty space with no guarantee of being seen. Yet here they arrive, completing a path billions of years long. Each photon reaching us is a meeting of past and present. The universe delivers its history in these small fragments, waiting for us to notice. There is another dimension to light, one that reveals itself only when we examine its relationship with matter in the finest detail. Every photon behaves both as a particle and a wave. It can travel across billions of kilometers as a wave of energy. Yet when it reaches an atom, it arrives as a single, precise packet. This dual nature puzzled early scientists and continues to challenge our understanding of reality. When a photon interacts with an electron, it can excite the electron to a higher energy state. In that moment, the boundary between matter and light becomes thin. Energy reshapes structure. When the electron falls back to its original state, it emits a new photon, carrying a signature of that transition. This constant exchange forms the basis of all illumination in the universe. In the vastness of interstellar space, these interactions occur at scales so small that they seem almost fragile. Yet from them arise the colors of nebulae, the glow of galaxies, and the soft radiance of starlight. The universe expresses itself through these exchanges. Every glowing cloud we see in telescopes is a conversation between atoms and photons. There is also the phenomenon of scattering, where photons are redirected by particles too small to see. This is why some nebulae glow blue, reflecting scattered starlight. It is why dust clouds can obscure the light from young stars, wrapping them in a soft, reddish veil. The universe paints its structures not only with matter, but with the journeys that photons take through that matter. In regions filled with magnetic fields, light behaves differently still. Photons can shift in energy or direction as they encounter magnetic lines that thread through space. These fields are invisible, yet their influence changes the paths of entire beams of light. Astronomers study these shifts to understand the unseen scaffolding that shapes galaxies. There is a deeper question behind all of this. Light not only illuminates matter, it reveals structure. It makes the universe observable. Without light, the cosmos would exist in silence, its beauty hidden in endless darkness. With light, every cluster, every star, and every world becomes known. This connection gives rise to a profound thought. What we observe depends on the light that reaches us, and our understanding of the universe is shaped by those photons. We do not see things as they are now, but as they were when the light left them. Observation becomes an act of time travel. In a quiet sense, light is the mediator between being and knowing. It links the existence of distant objects to the awareness of observers. When we gaze into the night sky, we are not merely looking outward. We are participating in the universe's own unfolding. Light, therefore, is not only a physical phenomenon. It is the bridge that joins matter, space, and consciousness. Its journey reveals that the universe is not an isolated structure, but a connected whole, where energy moves freely between creation and perception. Every photon carries a fragment of the cosmic story and completes that story within the mind that receives it. If we could watch light from above the cosmos, we would see its patterns like threads stretching across time. Some threads originate from quiet stars. Others burst from supernovae. Some drift through dust clouds, softened and reddened. Others travel untouched, perfect and unchanged. Every galaxy becomes a tapestry of light. The colors reveal age, temperature, and composition. Blue light marks the presence of young stars. Red light reveals older, more settled populations. In this way, light becomes a map of cosmic evolution. Galaxies glow in patterns that reveal their histories. Some pulse with furious creation. Others drift in peaceful decline. Even the night sky above Earth is a record of many ages. Ancient stars, young clusters, distant galaxies, and wandering planets all contribute their light to the same canvas. What looks simple is a composition built from billions of overlapping stories. Throughout all this, light remains consistent. Its speed never changes. Its behavior follows the same principles everywhere. It is the universal messenger, the thread that connects everything through time. And it is this reliability that makes it so powerful. Through light, we know what the universe is made of. We know how old it is. We know how it expands and evolves. In the end, the journey of light is a story of transformation. It begins in the heart of stars, travels across space, touches worlds, shapes life, and becomes awareness. It reveals the past and illuminates the present. It links us to everything that has ever existed. Humanity's understanding of the universe depends entirely on this traveler. Without light, the cosmos would be silent and unknowable. With it, the universe opens itself with clarity and grace. Each time you look at the night sky, you are witnessing a dialogue between past and present. The starlight that reaches your eyes tonight may have begun its journey before Earth formed. In that instant of seeing, the universe completes a cycle that spans billions of years. Light connects us not only to distant places, but to distant times. It teaches us patience, continuity, and wonder. Through light, the cosmos remembers itself, and through us, that memory becomes conscious thought. Every star that shines must one day fade, yet its fading is never a disappearance. Instead, it becomes a transformation so profound that it reshapes the very matter of the universe. The light that once burned in its core continues on, carried by the atoms it releases back into space. When a star reaches the end of its fuel, gravity slowly reclaims its ancient authority. The delicate equilibrium between outward radiation and inward pressure weakens. In this surrender, new wonders emerge. For smaller stars like our Sun, this transformation unfolds over billions of years. When hydrogen runs low in the core, fusion slows and gravity gently pulls the star inward once more. The outer layers respond by swelling, expanding into a vast sphere that glows with a softer, redder light. This phase is known as the red giant stage. The star becomes hundreds of times larger than before, its atmosphere drifting outward as gentle pulsations push gas away. These waves of material expand into space, forming delicate shells of color and symmetry that glow under ultraviolet light from the shrinking core. Astronomers call these shapes planetary nebulae. Though the name is misleading, the structures they create are breathtaking. Green, violet, blue, and crimson waves spread out like cosmic petals, drifting for tens of thousands of years before thinning into the dark of interstellar space. At the center of each nebula lies a small, brilliant remnant, no larger than Earth, yet heavier than the Sun. This remnant is a white dwarf, composed mostly of carbon and oxygen, packed together so tightly that a teaspoon of its matter would outweigh a mountain. A white dwarf no longer fuses atoms. It shines only from the heat stored within it, radiating its last warmth for billions of years. Eventually, it cools into a dark, cold object, a black dwarf, though the universe is still far too young for any to exist. These remnants are the quiet ghosts of stars. They drift silently through the galaxy, holding within their atoms the entire record of every fusion reaction that once lit their cores. Yet not all stars end their lives in such gentle beauty. The more massive a star is at birth, the more dramatic its final act becomes. Stars many times larger than our Sun race through their fuel at astonishing speed, living fierce but brief lives. In these luminous giants, nuclear fusion proceeds far beyond helium. Helium becomes carbon. Carbon becomes oxygen. Oxygen becomes neon, then magnesium, then silicon. Each new reaction unfolds in a shell around the core, like layers of an onion made of heat and pressure. Eventually, the star produces iron. Iron marks a boundary in the universe. It cannot release energy through fusion, so once the core fills with it, the star can no longer support its own weight. The core collapses in less than a second. Gravity overwhelms every last atom, crushing the heart of the star with unimaginable force. What follows is one of the most powerful phenomena known to science, a supernova. The collapse triggers a shock wave that explodes outward, tearing the star apart. For a brief moment, the supernova shines brighter than an entire galaxy, its light visible across millions of light years. It becomes a beacon of transformation, a cosmic firework announcing the end of one life and the beginning of many others. Within this explosion, temperatures soar to billions of degrees. In these final, violent seconds, the universe forges its rarest elements. Gold, silver, platinum, and uranium all arise from this extreme environment. Every grain of gold ever held in human hands was created in the death throes of a massive star. It is a reminder that beauty often comes from destruction, and that endings can be doorways into new creation. The blast of a supernova scatters heavy elements across the galaxy. These atoms mix with interstellar gas, enriching future clouds with the building blocks of planets, oceans, and life. Supernovae are cosmic gardeners, fertilizing the soil from which new stars arise. What remains at the core of a massive star after the explosion depends on its mass. If the leftover core contains between about 1 and 3 times the mass of the Sun, it becomes a neutron star. This object defies comprehension. It is barely 20 kilometers wide, yet its mass is so immense that a teaspoon of its material would weigh billions of tons. Neutron stars are strange worlds of pure density. Their atoms are crushed so tightly that protons and electrons merge into neutrons. The surface is as hard as steel, and the gravity is immense enough to bend light around it. Some neutron stars spin rapidly, emitting beams of radiation that sweep across space like cosmic lighthouses. These are known as pulsars. But if the core is even more massive, gravity presses past every limit. Nothing can stop the collapse. The core shrinks until it becomes a point of infinite density, hidden behind a boundary where not even light can escape. This boundary is called the event horizon. The object behind it is a black hole. Black holes are not empty spaces, but regions of extreme curvature in space-time. They anchor galaxies, govern the motion of stars, and shape the flow of matter. Though invisible, they reveal themselves by how they influence everything around them. Across the universe, neutron stars and black holes serve as reminders that destruction and creation are intertwined. A star's death is not a failure of nature, but a necessary part of cosmic evolution. Without these final acts, the universe would remain simple, filled only with hydrogen and helium. Instead, through millions of cycles of birth and death, the galaxy becomes richer. From these processes arise planets with iron cores, seas with salty water, and living beings capable of observing the stars that made them. Not all stars meet such dramatic fates. The smallest stars in the universe, known as red dwarfs, burn so slowly that none have yet reached the end of their lives. They may shine for trillions of years, longer than the current age of the universe by far. When they finally exhaust their fuel, they will cool quietly, fading into cosmic stillness without explosions or nebulae. Their passing will be subtle, almost gentle, like embers dimming after a long night. To understand the legacy of dying stars, we must look beyond a single life and toward the vast cycles that shape the galaxy. A star does not simply end. It becomes part of a continuum that stretches across billions of years. Each transformation adds new layers of complexity to the cosmic landscape. As the remnants of ancient stars drift through interstellar space, gravity begins its work once more. Even the faintest clumps of matter attract their surroundings, gathering dust and gas the way raindrops gather moisture in a cloud. These subtle motions mark the early steps toward the next generation of suns. Within these forming clouds, heavy elements forged in supernovae enrich the mixture. Carbon, oxygen, silicon, iron and countless other atoms blend like ingredients waiting for heat. This enriched material is essential for creating planets both rocky and gaseous. Without the deaths of earlier stars, Earth would have no continents, no oceans, no life. The calcium in bones, the nitrogen in DNA, the iron in blood, and the gold on a finger all originate from stellar furnaces long extinguished. In a very real sense, stars are the alchemists of the universe. As enriched clouds collapse, they form disks around newborn protostars. Over millions of years, particles within these disks collide and adhere, forming larger bodies. Some become asteroids. Some grow into dwarf planets. Some accumulate enough mass to form full worlds. This process, known as accretion, is slow but relentless. Each collision releases energy, heating the young worlds from within. In time, their surfaces cool, forming crusts, oceans, atmospheres, and magnetic fields. The early solar system was a chaotic place. Countless impacts shaped young planets, carving craters and forming moons. Comets delivered water and organic molecules. Asteroids redistributed metals and minerals. Amid this chaos, stability gradually emerged. Earth developed conditions suited for chemistry to flourish. In warm seas, energy and molecules combined to create the earliest forms of self-replicating life. But even in this phase, stars remain the central architects. The sun's steady light provided the energy needed to drive photosynthesis, weather cycles, and evolution. The gravity of the sun stabilized Earth's orbit, ensuring long-term conditions suitable for complex life to emerge. Other stars perform similar roles in their own systems. Across the galaxy, planets circle their suns, receiving energy that shapes their landscapes and climates. Where conditions align, life may emerge again, built from the same cosmic ingredients found here. The connection between stars and life is profound. Every heartbeat depends on iron forged in a collapsing star. Every breath depends on oxygen created in the core of a long-dead giant. Even the carbon atoms that make consciousness possible were once part of nuclear reactions millions of years before Earth formed. Because of this, the universe is often described as a vast recycling system. Matter is never wasted. It changes form, moves through time, and finds new purpose in each transformation. Modern astronomy has revealed these patterns with extraordinary clarity. By observing starlight, astronomers can identify the exact mixture of elements in different regions of the galaxy. Certain clouds contain high levels of heavy elements, indicating that many generations of stars have lived and died there. Younger regions, especially in the outskirts of galaxies, contain mostly hydrogen and helium, revealing that fewer supernovae have contributed to their enrichment. In this way, the chemistry of space becomes a map of its history. Each cloud, each cluster, each nebula carries a story told through its atoms. Simulations run on supercomputers recreate these cosmic cycles. Models follow billions of particles of gas and dust as they flow through the gravitational currents of a galaxy. They show how star formation accelerates in some places and fades in others. These simulations reveal a surprising truth. Galaxies behave almost like living systems. They breathe, expand, contract, and respond to their environments. Stellar birth and death act like a heartbeat, pulsing through their spiral arms and central bulges. At the core of many galaxies lies a supermassive black hole. Far from being passive, these central objects regulate the galaxy's evolution. They release jets of radiation and streams of charged particles that heat surrounding gas, affecting how quickly new stars can form. In this strange way, black holes enhance cosmic stability. Their immense gravity shapes the orbits of stars and influences the very structure of the galaxy. Though they are born from destruction, they play a crucial role in maintaining order. The Milky Way, our home, contains these same rhythms. Spiral arms filled with gas give rise to clusters of young stars. Older stars drift outward over time, forming halos and thick disks. Remnants of ancient supernovae enrich the regions where new stars form, ensuring that each generation becomes more complex than the last. Even our Sun has a story written in this pattern. It formed about 4.6 billion years ago, in a cluster with thousands of siblings. Most of those siblings have long since drifted away, scattered across the galaxy. The early solar system was shaped by powerful forces. Radioactive elements created in past supernovae warmed the young Earth from within. Heavy metals gathered at its center, forming the core that powers Earth's magnetic field. This field protects the atmosphere from solar radiation, making life on the surface possible. Every layer of Earth's structure carries the memory of stars. Crustal rocks contain elements born during stellar collapse. Oceans hold hydrogen from the beginning of time and oxygen from ancient stellar fusion. Even the air contains nitrogen shaped in the remnants of giant stars. Life emerged from this stellar heritage. Simple molecules assembled into complex chains, forming the earliest cells. Over billions of years, evolution unfolded in response to sunlight, climate, and geology. Through this slow transformation, consciousness eventually emerged. When we reflect on our own existence, we trace our origins not only to Earth, but to the cosmos itself. Human life is a continuation of processes that began long before there were planets or stars. We are the universe becoming aware of its own history. The death of stars also influences worlds far beyond Earth. Supernovae create shock waves that compress gas clouds light years away, triggering new rounds of star formation. These waves travel across the galaxy like ripples, spreading through a vast ocean. In this cycle, destruction becomes a catalyst for creation. It ensures that the galaxy never stagnates, that matter continues to rearrange itself into new patterns of light and life. This is the cosmic balance that governs everything from atoms to galaxies. Even black holes, often imagined as pure absence, play crucial roles in this balance. When material falls into their gravity, immense amounts of energy are released. Jets blast outward, energizing gas clouds and shaping star formation for millions of years. Seen from this perspective, the universe is not chaotic. It is a system governed by cycles that repeat in different forms, but always follow the same underlying principles: birth, growth, transformation, and renewal. Astronomers studying distant galaxies can determine their ages by examining the types of stars within them. Galaxies filled with young blue stars are still forming new light from fresh clouds of gas. Older galaxies glow red, their fuel depleted, transitioning into quiet cosmic retirement. This color shift acts like a clock, marking the passage of time on a scale far beyond human experience. In the red glow of ancient galaxies, we see the slow cooling of cosmic energy, the gradual transformation of matter into new forms. Our own galaxy sits somewhere in the middle of its life. It is still forming stars, still recycling matter, still glowing with the combined radiance of hundreds of billions of suns. Within it, The sun shines calmly, a stable light in a universe full of extremes. The energy it emits sustains every form of life on Earth. Every heartbeat, every breath, every thought depends on photons born in its core. In this sense, the sun is not only a star, but the ongoing link between humanity and the cosmos. When we acknowledge this connection, the death of stars becomes something meaningful rather than tragic. Each dying star contributes to the unfolding complexity of the universe. Its atoms become part of planets, oceans, and organisms. Its energy shapes environments and fuels evolution. The story of stellar death is therefore also the story of cosmic continuity. Nothing is wasted. Everything reappears in new forms, carrying forward the memory of light. Somewhere in the galaxy, new stars are forming right now. Their light will not reach us for thousands of years. By the time we see them, their planets may already exist. Their systems may already be thriving. Each star born today is part of a chain that stretches back to the earliest moments after the Big Bang. In this chain, our own existence is a single link, fragile but luminous. Through us, the cosmos continues to explore itself. When we look at the night sky, we are witnessing a timeline of creation. Light from young stars, ancient stars, and dying stars all reaches us at once. The sky is a mosaic of time, a living memory written in photons. The atoms within our bodies have traveled through that mosaic for billions of years. They have survived explosions, drifted across interstellar space, and taken part in new formations again and again. To exist is to participate in this vast lineage. As Chapter 5 closes, the story of stellar death reveals itself as something much greater than destruction. It is a reminder that the universe evolves through cycles of renewal. Matter, energy, and light flow endlessly from one form to another. In this cycle, stars are both the beginning and the continuation. Their lives create the conditions for new worlds, and their deaths enrich the universe with the ingredients for life. Through them, the cosmos remains alive with potential. There is a moment each night when the world settles into quiet. The air cools, shadows lengthen, and above us the first stars appear, like ancient memories rising from the horizon. They seem still, eternal, untouched by time. Yet each one carries the entire history of creation within its light. When we look upward, we are not simply seeing stars. We are witnessing the universe remembering itself. Every point of brightness is a message from the distant past, arriving here after a journey that may have begun millions or even billions of years ago. In that glow lies everything: the birth of matter, the flow of time, the long story of how simplicity became complexity. Starlight reveals a universe that is never still but always unfolding. To stand beneath the night sky is to look backward through cosmic time. The light we see began traveling long before human beings existed. Some of it left its star before Earth formed, before the oceans rose, before life took root. Some of the starlight reaching us tonight comes from suns newly born in clouds of dust. Some comes from aging giants nearing their final transformation. Some comes from galaxies so distant that their light began its journey when the universe was still young. All of it converges in a single moment of seeing. When that light touches our eyes, we participate in a connection that spans the entire cosmos. It is a reminder that every atom in our bodies shares the same origin as the stars above. We are made of the same materials and shaped by the same laws. The universe, as it turns out, is not a collection of isolated objects. It is a great continuity, a flowing system of energy and matter evolving through time. Gravity links planets to stars, stars to galaxies, and galaxies to the fabric of space-time itself. We are not outside this system observing it from a distance. We are inside it, expressions of the same cosmic pattern that forms nebulae, oceans, cells, and thought. To see the stars is to see a reflection of our own origins. Their light touches oceans, forests, mountains, and the surfaces of our eyes. It scatters through the atmosphere, bending into the colors of sunrise and sunset. It threads through water and stone, awakening life and shaping the rhythm of the planet. Every sunrise is a retelling of creation. Every sunset is a gentle reminder of the cycles that govern the cosmos. In these daily patterns, we glimpse the same forces that guide the birth and death of stars. Science describes this story with elegant clarity. Energy moves from one state to another, always conserved, always transformed. Hydrogen becomes helium, helium becomes heavier elements, and those elements become worlds. Dust becomes star, star becomes life, life becomes awareness. In every form, energy changes but never ends. This principle, the conservation of energy, connects the smallest atom to the largest galaxy. The light that leaves a star today may one day warm a planet, stir its winds, or fuel the growth of living organisms. Energy flows through the cosmos like a slow, continuous river. If we listen to the universe through this idea, we hear rhythm rather than chaos. Destruction and creation are not opposites, but phases of the same cycle. Stars collapse so that new stars may rise. Worlds end so that others can form. Human life follows these same patterns on a smaller scale. We change, grow, age, and return our energy to the world around us. Our breath becomes part of the air another breathes. Our warmth flows outward as light and heat. This cycle gives meaning to impermanence. To live within change is to live as the stars do, bright for a moment, but part of something far larger and enduring. Our individual stories become chapters in a cosmic book that never stops being written. Astronomy, though built on measurement and observation, is ultimately an act of wonder. When we study the stars, we search not only for facts, but for context. We seek to understand where we come from, what we are part of, and how everything connects. Every discovery deepens that sense of belonging. We once believed the Earth was the center of the universe. Then we learned it is one planet among many, circling an ordinary star in a vast galaxy. Instead of diminishing us, this understanding expands our story. The scale of the cosmos is immense, yet strangely familiar. Between stars lies the material of future worlds, the dust of possibility. Every grain of that dust holds the potential to become light again. In that sense, the universe is always beginning. Creation is not a moment of the past, but a continuous act that unfolds everywhere at once. Even now, deep in regions unseen, new stars are forming in silence. This perspective brings comfort when we consider our brief lives. Though our time is small on a cosmic scale, we belong to a story that spans billions of years. The atoms within us have lived through countless cycles of birth and death. They are older than the sun, older than the galaxy, older than Earth itself. We carry history not in memory, but in matter. To breathe is to continue a process that began long before life emerged on any world. To think is to shape starlight into awareness. Perhaps this is why starlight feels peaceful. Its presence speaks of endurance without hurry. of vast time held gently in the present moment. In the quiet shine of a star, we sense continuity rather than distance. When we turn off our lights and look upward, the universe looks back, not through intention, but through reflection. We are composed of the same atoms, guided by the same laws. Through us, the universe becomes able to observe its own unfolding. There is humility in this realization, yet within it lies a kind of hope. It suggests that awareness, compassion, and creativity are not accidents. They are expressions of the same order that shapes galaxies, stars, and living worlds. Life, in all its fragility, is one of the ways the universe explores its potential. We are not separate from the stars. We are their continuation. Their history flows through us, written in bone, breath, and thought. Stars also teach us patience. Their light travels across unimaginable distances, crossing time and silence without complaint. Even when clouds block our view, the light continues forward, steady and unbroken. We, too, are travelers in time. Our journeys may be shorter, but they follow the same principles. Every moment is part of a larger continuum. In the end, the universe does not hurry. It unfolds in perfect rhythm, balancing stillness with motion, creation with transformation. When the first stars formed, there were no eyes to witness them. Now, through us, their light is seen. Through our curiosity, their story continues. Through our understanding, the cosmos learns something new about itself. The atoms in our bodies once drifted between galaxies. They journeyed through supernova, cooled in clouds of gas, and were shaped into molecules on a young world. Each one carries a trace of that long history, a record of the universe's endurance. To exist is to participate in a miracle of persistence. We are not outsiders looking in. We are chapters in the same cosmic story. Every heartbeat echoes the cycles that govern stars and galaxies. The remnants of stellar death drift quietly through space. Some travel alone, wandering for millions of years before meeting other particles of dust. Others gather into slow-moving currents shaped by gravity, swirling through the galaxy like faint tides of matter. Within these flows, the ingredients of future stars and worlds move endlessly, waiting for the next moment when gravity will draw them into a new cycle of creation. As these enriched clouds accumulate, something remarkable happens. Elements heavier than helium begin to play a larger role. Carbon, oxygen, silicon, and iron increase the efficiency with which the gas cools. Cooler gas collapses more easily under its own weight, making star formation more likely. In this way, the lives and deaths of earlier stars directly influence the birth of later generations. Nothing in the cosmos exists in isolation. Everything is linked through a chain of cause and continuity that spans billions of years. As clouds cool and contract, dense knots form deep within them. These knots become the seeds of new suns. Each one begins as a faint glow in infrared wavelengths, hidden within a thick veil of dust. From the outside, the cloud may appear dark, yet inside it is alive with the first stirrings of new light. The dust itself plays a protective role, shielding the growing protostar from the disruptive radiation of nearby stars. This keeps temperatures low enough for matter to gather smoothly toward the center. Within these collapsing knots, turbulence gradually settles into rotation. As the cloud spins, material flattens into a disk that circles the forming star. This disk is the birthplace of planets. Minute grains of dust collide, stick together, and slowly grow into larger structures. What begins as particles smaller than a grain of sand will one day become mountains, oceans, and continents. There is something humbling in this slow assembly. Worlds are not born in moments of drama, but in countless quiet collisions over vast stretches of time. Planet formation follows a path shaped by both order and chaos. Random impacts lead to larger bodies, while the gravity of the growing star shapes the overall structure of the system. Some regions of the disk become warm and rocky, suitable for terrestrial planets. Others remain cool and rich in volatile substances, forming gas giants or icy worlds. This diversity arises naturally from the interplay of distance, temperature, and chemistry. In the early solar system, collisions were violent and frequent. The Earth itself grew through such impacts, gathering mass from countless smaller bodies. One especially massive collision likely formed the Moon, scattering molten material into orbit that later condensed into a companion world. Even now, remnants of that era drift in the form of asteroids and comets, silent archives of the solar system's youth. The materials that make up these young worlds carry the signatures of ancient stars. Deep within the Earth's core lie elements forged in supernova ashes. In the crust, minerals hold atoms that traveled across interstellar space long before the planet formed. Every mountain, every grain of soil, every breath of air is composed of matter created in stars that lived and died long before the sun existed. The universe is a recycler of extraordinary elegance. Nothing is wasted, and everything is transformed. Water, the element essential for life on Earth, also carries a cosmic heritage. The hydrogen in water traces its origin to the first moments after the universe began. The oxygen was forged later in massive stars and released into space when those stars exploded. When these atoms met and combined on the early Earth, they created a substance that would become the foundation of oceans, weather, and biology. In this way, life emerged from a dialogue between ancient processes and planetary evolution. Life itself is another cycle of transformation. The first molecules capable of copying themselves formed in an environment shaped by volcanic heat, chemical reactions, and the steady energy of starlight. These molecules assembled into early cells, which evolved into more complex organisms. Across billions of years, life diversified into the immense variety we see today. Yet, at every level, from cell to species, it remains a continuation of cosmic history. The atoms of life hold memories of supernova and stellar winds. As organisms grew more complex, they developed senses that allowed them to interact with their environment. Vision itself is an adaptation to starlight. Eyes evolved to detect photons arriving from the sun, converting ancient energy into biological information. In this way, living beings became participants in the journey of light, turning physical radiation into perception. Human consciousness is part of this same continuum. The brain is an intricate network powered by chemical and electrical signals, each one shaped by the flow of energy that began in stellar cores. Thought arises from processes that can be traced back to the fusion of hydrogen in ancient suns. Our awareness is not separate from the cosmos, but one of its many emergent expressions. Through consciousness, the universe observes itself, remembers itself, and questions its own origins. The fact that we can contemplate the life and death of stars is a testament to the continuity that binds matter and mind. We are not outsiders looking inward. We are extensions of the very processes we study. To understand stellar evolution is to understand something fundamental about ourselves. Astronomers use technology to decode this continuity. Spectroscopy reveals the elements present in distant stars. Telescopes capture light that began its journey before the Earth existed. Space probes and observatories allow us to see the universe across every wavelength, from radio waves to gamma rays. Each instrument adds another layer to our understanding of cosmic history. Yet for all the precision of scientific observation, there remains a sense of awe in the face of the universe's complexity. No matter how much we measure, there is always more to discover. The cosmos is not a completed story, but an unfolding one. Stars continue to be born, evolve, and die. Galaxies merge and reshape one another. Black holes grow and influence the motion of entire regions of space. Even now, the Milky Way is changing. Stars orbit its center in vast cycles that take hundreds of millions of years to complete. Gas clouds move slowly through its spiral arms, gathering, collapsing, and igniting. The galaxy is not a fixed structure, but a dynamic system in perpetual motion. In a few billion years, the Milky Way will merge with the Andromeda Galaxy. This merger will reshape both galaxies, triggering new waves of star formation as gas clouds collide and compress. Despite the dramatic scale, individual stars are unlikely to collide directly. The distances between them are too vast. Instead, their collective gravity will sculpt new structures and new patterns of light. The cycles of stellar death and birth continue on every scale. In star-forming regions, young suns shine brightly, the radiation heating the surrounding gas. Nearby, older stars reach the end of their lives, releasing material that will one day become part of new systems. This rhythm nourishes the universe, ensuring that creativity never ceases. Through this process, the universe moves toward greater complexity. From simple elements came stars. From stars came heavier elements. From those elements came planets, oceans, and living beings. Each step built upon what came before, adding layers of structure and possibility. When we look at a night sky filled with stars, we are watching this story unfold. Some of the light we see began its journey when early life on Earth was still forming. Some comes from stars that no longer exist. The sky is a mosaic of time, stitched together by photons carrying the memories of their origins. To understand stellar death is not to dwell in darkness, but to appreciate renewal. The universe is constantly letting go of what was to make room for what will be. In every supernova, there is both an ending and a beginning. The ashes of old stars become the seeds of new ones. The cycle never stops.